So in Chapter 5, Section 5, we're going to be talking about U-substitutions. So U-substitution is the chain rule backwards. So that raises the question, how are we going to use the chain rule backwards? So let's start with an example. So how do we find the integral of, if we have the integral of x squared cosine x cubed dx. So a couple of things we want to take note of is inside of our cosine function right here, this is function composition. So when we have function composition, this is a telltale sign that we are going to need to do a U-substitution, because the U-substitution undoes the chain rule, and the chain rule was how we took the derivative of something with composition. And since derivatives are inverses of each other, U-substitutions are the inverse of the chain rule. So when we see composition, that's going to be a strong indicator that a U-substitution is probably in our future. So let's start with the derivative and see if we can work our way backwards. So what is the derivative of y equals sine x cubed? So let's identify this as a composition. So then our f of u would be sine u and our u is going to be x cubed. So then our y prime by the chain rule would be df du times du dx. So that would give us the derivative of sine is cosine u times du dx, which is going to be 3x squared. And then putting all those together, we get 3x squared cosine u, which is x cubed. And we'll notice y prime is almost the same as the integrand. So let's write all of this out again together. So we have the integral of x squared cosine x cubed dx, and I'm going to use the Leibniz notation, and we have then our derivative dy dx is the same as 3x squared cosine x cubed. So this is one of the situations where the Leibniz notation really shines. We can treat our derivatives in Leibniz notation as a fraction. So we can solve this for dx. So if we wanted to solve that equation for dx, we would multiply both sides by dx, and that gives us dy is equal to 3x squared cosine x cubed dx, and then we would divide by 3x squared cosine x cubed, but if I do it on one side, I have to do the same thing to the other. So now after all of that, we get that dx is equal to dy divided by 3x squared cosine x cubed. So if we substitute dx with what it's the same as, and we substitute in the original y, or the u rather, we're going to get the following. So we substitute this into our integral. So we have the integral of x squared cosine x cubed and then we substitute in our dx, which is now dy over 3x squared cosine x cubed, and a miracle happens. The x squareds reduce out and the cosine x cubes reduce out. We have a constant of 3 in the denominator. So since it's in the denominator, we pull it out in front of our fraction, or out in front of our integral as a fraction of 1/3. And the only thing that's left is now dy. So after substituting this in, the integral of x squared cosine x cubed dx is equivalent to 1/3 times the integral of dy. Well, we know how to do that integral, so this is going to be 1/3 y plus an arbitrary constant. But what was y when this whole thing started? Y is sine x cubed. So we substitute back in and we get 1/3 sine x cubed plus c. So the antiderivative of x squared cosine x cubed is 1/3 sine x plus c. And we could check once again by taking the derivative and seeing that we get back the integrand. So this was just an example to show you kind of how everything works. So let's dig into the details and we'll come up with some algorithms to help us out when we're trying to work these problems. So this is the big idea, is that we're trying to use the chain rule backwards. When we do so, we call it a U-Substitution. All right, so here is our theorem for our U-substitutions. So the U-substitution rule for indefinite integral states if u, which is equal to g of x, is a differentiable function whose range is an interval I and f is continuous on I, then the composition So the integral of the composition f composed with g times g prime of x dx is equal to the integral of f of u du, or the integral of f of u du dx times dx. And notice like what happened, our dx's will reduce out, and we get a new integral in terms of the new integral u. So the big idea is we started with a function of one variable, x, and after using the chain rule, we substituted out and we converted from a function of x to a function of a new variable. When we do so, what our theorem is saying in symbols is when we are done, like what we see right here, there will only be the new variable u, or as we did in the previous example, y, present in the integral. So that's the first thing we need to be on the lookout for. If we would have done this step where we solved for dx and we substitute in, and then in the next step, notice what happened. All of the functions involving x reduced out. If that doesn't happen, that means we picked the wrong substitution, and we would have to go back to picking this, which we didn't really do. I just gave it to you this time, and we'll talk about how to pick them. But we would have to go back to this step and start the process all over again. So that was the U-Substitution rule for indefinite integrals. The same thing applies for definite integrals, but when we do the U-Substitution, it changes the limits of integration. So if our integral starts with the limits of integration from a to b, those are x values. When we do our U-Substitution, we have to change them. Just like what happened up here, we changed everything from x's to y's. We would need to change our limits of integration by putting them into the function that we're substituting and get new limits of integration. So when we do a U-Substitution, it doesn't only change the integrand. If we have limits of integration, it will also change those to the new values. All right. So this next one is just a printed example to help us visualize what's happening here. So example number 1 is we have the integral from 0 to pi over 2 of sine x cosine cubed x dx. So in this example, we're going to choose to let u equal cosine x. If we do, then the derivative, we'll write it in terms of a differential, like what we did back in chapter 4. So this is the differential. So then du, the derivative of cosine is negative sine, so du is equal to negative sine x dx. And then we will notice in this case we have sine x dx, which we would also have in the original. So sine x dx is then equal to negative du. So if we replace the sine x dx with a negative du, and then we have our cosine is u, so then that would become a cosine cubed would become u cubed negative du. We also have to use the U-Substitution to change our limits of integration. They are originally 0 and pi over 2, so we put those in for the x values in cosine. So we would have the cosine of 0, which gives us 1, and the cosine of pi over 2, which gives us 0. Pulling the negative sign from the du out in front, we would have the negative of the integral from 1 to 0 of u cubed du. And if we reverse the limits of integration, we have the property of integrals. The integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. So we reverse them, and we get the integral from 0 to 1 of u cubed du. So when we started, we knew that the indefinite integral was the area underneath the curve. So if we graph sine x times cosine x from 0 to pi over 2, that's going to be this picture right here. That's the area underneath the curve in that picture. Well, after we change our limits of integration, we now have the new integral from 0 to 1 of u cubed du. These two graphs have the same area under the curve. So what we're really doing when we do a U-substitution is we are changing the shape geometrically of one curve into another curve. So we transformed the function sine x cosine x on 0 to pi over 2 to a function that has the same area underneath the curve on the interval 0, 1. So what we're doing when we substitute out the differential is the differential tells us how the shape is changing, and that's what the negative du equals sine x dx was doing. So it's kind of an interesting idea that we are geometrically changing something into something else so that we can find the area underneath the curve. All right, so I know that's a lot of information. That's the big picture. So now let's focus in on some specific examples on how we are going to do this. So we're going to go from big picture to some very specific examples for doing U-substitutions. All right, so let's take a look at example number 2. So we have the indefinite integral 2x e to the x squared dx. And we want to find the antiderivative. So, as mentioned at the beginning, U-substitution is the chain rule being used backwards. So a good place to look to start is we always want to look for something that is inside something else, aka composition. So when we look at 2x e to the x squared, what function is inside something else? Well, we have an e to the x composed with x squared. So our x squared is our inside function. So we pick u equal to x squared because u equals x squared is inside e to the u. So if I have e to the u, but u is equal to x squared, that would give me e to the x squared. Another thing that strongly suggests that that is the right pick is the fact that the derivative of u, so du, is going to be 2x, which is also in the integrand. So we calculate the differential, and that gives us du dx is equal to 2x, And that would say then that du is equal to 2x dx by multiplying both sides by dx. Then if we solve for our dx, we divide by 2x, we divide by 2x, and this gives us that du over 2x is equal to dx. So now that we've solved for the differential, we substitute dx into the integral. So when we do so, we have 2x e, and we substitute in our u, times dx, and our dx is going to be the same as du over 2x. And we notice then that the 2x and the 2x reduce out, leaving us with the integral of e to the u du. So we should note at this point the integrand should only contain the variable u after substitution and reduction. If there are both x's and u's, the u is incorrect. So then you would have to, we would need to start over. With a different u. So we'll notice what this is saying is when we did this, our x's both reduced out, which was good, and after our reduction, we had an integral now that was a function of only u, and there were no x's left. If we would have had a mixture of both x's and u's, we have an error somewhere, and we would have to go back and see what had happened. All right. So now we need to finish. So we have the integral of e to the u du. Well, e to the u is an easy integral. We know that the integral of e to the x is e to the x, so the integral of e to the u is e to the u plus c, and then we substitute out our u, so we have e to the u, but our u was x squared plus c. So we substitute out back our original substitution, and we get e to the x squared plus c. It's also worth noting we can check our solution by taking the derivative. Remember, derivatives and integrals are inverses. So if I take the derivative d dx of e to the x squared plus c, well, my derivative of e to the x is going to be e to the x squared. Then by the chain rule, I multiply by the derivative of the inside, and the derivative of x squared is 2x, plus the derivative of a constant is 0. So we get 2x e to the x squared, which is exactly the integrand that we started with, 2x e to the x squared. So we can check our integrals by taking the derivative and seeing that we get what we started with, because derivatives and integrals are inverses. So we should always get the original integrand because derivatives and integrals are inverses. So they undo each other just like addition and subtraction or multiplication and division. All right, let's keep going. So once again, we want to find the integral from e squared to e to the 7th of 1 over x ln x dx. And this is a little different than the previous one. The previous example was an indefinite integral, and this one is a definite integral. We also are trying to find something that's inside of something else. Well, this one's a little bit harder to see, but we actually have the natural logarithm inside the reciprocal function. The other hint that is helpful in letting us know that what we want to pick for u is we are looking for something, and what we saw up here is we picked u to be x squared because its derivative 2x was in the integrand. When we look at r's, if we wanted, we could rewrite it this way to make it more explicit. The derivative of the natural logarithm of x is 1 over x, which is present in our integrand. So this would suggest that we pick our u to be the natural logarithm of x. And if we do that, we then get that du is equal to 1 over x dx. And if we solve for dx, we're going to get x du is equal to dx. So now it's time for us to substitute everything in to our integral. So we have the integral, but when we have a definite integral, remember we have our old limits of integration, which are x's. We need to change them to be in terms of u's. So we're going to plug each of these into our U-substitution. So our new limits of integration are going to be the natural logarithm of e squared, and our upper limit of integration is going to be the natural logarithm of e to the 7th. And just to be very, very explicit, this is u of e to the 7th and this is u of e squared using our u function that we have over here. And then we have 1 over x. Well, ln x is the same as u, so times u, and then our dx is x du. So now we reduce out. Notice, as is supposed to happen, our x's reduce out, and we simplify. The natural logarithm and e are inverses, so they reduce out, and the natural logarithm and e in the lower limit of integration are also inverses, so e and the ln cancel, giving us 2. The e and the ln cancel, giving us 7, and we're left with 1 divided by u du. So after doing our u substitution, we now have the new integral from 2 to 7 of 1 over u du. So if we look at our antiderivative sheet, we have 1 over x, and the antiderivative, or the integral of 1 over x dx, is the natural log of the absolute value of x. So this is going to be the natural logarithm of the absolute value of u plus c, but our u is the natural logarithm of x, so the natural logarithm of the natural logarithm of the absolute value of the natural logarithm of x plus c. So we have the natural logarithm of the natural logarithm of x plus c is our antiderivative. Oops, I'm not doing plus c's this time because we have a definite integral. So we have our limits of integration go from 2 to 7. So if we evaluate this, from 2 to 7, we're going to get the natural logarithm of 7 minus the natural logarithm of 2. And since the absolute values of 7 and 2 are 7 and 2 respectively, we have ln 7 minus ln 2 would be our solution. All right. So now, you guys have been watching me do these for long enough. It is time for us to work on a U-try. So to do this U-try, we need to pick our U value. So the U that we're going to want to pick this time is what's on the inside, which is the e to the x. So if we pick u equals e to the x, then du is equal to e to the x dx. And if we divide by e to the x and divide by e to the x, we get du over e to the x is equal to dx. So then we substitute into our integral. So we're going to have e to the 0 and e to the natural logarithm of pi. And then our e to the x becomes a u. So we have our e to the x cosine u, and then our dx is du over e to the x. Our e to the x's reduce out, and we get the integral. So e to the 0 is 1. The e and the natural log reduce out, and we get a pi. And we have cosine u du. So we take the antiderivative of cosine as negative or as positive sign, and we evaluate that from 1 to pi, and that gives us sine pi minus the sine of 1, and the sine of pi is 0, so we get 0 minus sine 1, which is the negative of the sine of 1. And that is going to be our solution. All right, so I want to work this problem again because there's another common way for people to do U-substitutions. And I know we're probably not going to the tutoring center and stuff, but I want you to at least see this so if it comes up next semester, you're not like, what the heck are they doing? They are mathematically equivalent, so you only have to be able to do these one way. But let's take a look at this again and see a slightly different method to accomplish the same task. And if you think about it, you'll discover that they are exactly the same thing. So there's not any trickery going on. It's just two different ways to think about the same thing. So our u substitution wouldn't change. We would have u still equals e to the x, and du is equal to our derivative of e to the x is still e to the x dx. But we'll notice that e to the x is the same as u. So then we would have du is equal to u dx. And then we could divide by u, and we still have dx by itself. So we have du over u is equal to dx. So notice this is really the same thing we had up here, du over e to the x, because what's e to the x? U. So we substitute that out, and we do the same thing. So we would have e to the 0 and e to the ln of pi, and then e to the x would be u. So we would end up with u cosine u times our dx, which is du over u. Those still reduce out, and at the end of the day, we end up with the same integral that we had. So just a slightly different way to do it, but a lot of people, oftentimes you will be able to substitute out your U-substitution into your differential. And this is a helpful thing, and we'll actually use it later on. But just be aware there's more than one way to do these. So it's kind of like trigonometric identities. There's going to be 3 or 4 different ways to get from A to B. As long as you don't break any algebra rules or any calculus rules, you'll get the same answer in the end. So think of it more as I'm showing you a path. I'm not showing you the path, because there's more than one way to get from A to B. So this is one of the things that makes derivatives and integrals very different. With derivatives, we had a definite rule that took us definitely from this to this. With integrals, there is, how should I say, a little more flexibility. There are more paths to get from A to B. And that can be both a good thing and a bad thing, as we'll see. So pros and cons, but it is what it is. So just be aware that somebody might be doing this completely different from you and getting the same correct answer at the end. And if that's the case, they just found a different path, and that's okay. All right, let's keep going. So let's take a look at our next example. So we take a look at example 4, and what do we think is inside of something else? Well, we have a fifth power function, so we have a 5x minus 3 on the inside. So we're going to pick that as our u. Then our du is going to be 5 dx. Divide by 5, and that gives us that du divided by 5 is equal to dx. So we substitute into our integral, and we get u to the fifth power times du over 5. So that's 1/5 times the integral of u to the fifth du. So that's 1/5 times the antiderivative of u to the fifth is u to the sixth over 6 plus c. So 5 times 6 gives us 30. So we have 1/30th u to the sixth plus c, but our u is 5x minus 3 to the sixth plus c. So that would be our antiderivative. If you didn't want to use a U-substitution, we could do this problem a different way, right? But that would entail having to multiply out 5x minus 3 5 times, right? So we'd have 5 of those factors, and we'd have to distribute all of that out, and it turns into a nightmare. But if you did manage to multiply all of that out, you could then do integration term by term, and you would get an equivalent correct answer. It would just be more work than is reasonable for us to do. All right, so the next thing we're going to look at is another U-try. For U-try number 2, we're going to want to make a U-substitution for each of these. So in our first one, we pick u equals to 3x, and then that's going to give us du is equal to 3 dx, and we divide by 3, divide by 3, so that would give us that dx is du divided by 3. We substitute that into our integral, and we get e to the u times du over 3, or 1/3 the integral of e to the u du. So that gives us 1/3 e to the u plus c, which is 1/3 e to the 3x plus c. And if we do something very similar on our next one, if we let u equal negative 2x, then du is negative 2 dx. So that would give us that dx is negative du over 2. So we would have the integral e to the u again, this times negative du over 2. So that would give us negative 1/2 times the integral of e to the u du, or negative 1/2 e to the u, but our u is negative 2x plus c. And then lastly, we would have u equals 17x plus 5. So then du is 17 dx, and our dx is du over 17. So we would have the integral of e to the u times du over 17, which is 1 over 17, the integral of e to the u du, which would give us 1/17 e to the u plus c, so 1 over 17e, 17x plus 5 plus c. So if we look at each of these, we'll notice something that happened. So after we made our u substitution, in each of the 3 cases, we ended up integrating some constant out in front, the integral e to the u. And the integral of e to the u was e to the u. The next thing we noticed that the constant out in front was always the derivative of the exponent. It turns out that this pattern holds with this caveat. When u is a linear function, we have the following. That the integral of f of u dx is going to be capital f of u divided by, I'm making this more complicated than it needs to be. Let's just do the specific case that we had here, mx plus b dx. It's going to be 1 over m e to the x plus c. We can generalize this into our next set of examples. So we're going to be doing something very similar here. In fact, we'll notice that the linear functions in this row are exactly the same as the ones that you guys just did. So in this pattern, we're going to be finding our antiderivative of our outer function as sine is going to be negative cosine. So we would have the antiderivative of sine is negative cosine 3x, but now we have to divide by the derivative of 3x, which is 3 plus c. Here we're going to have cosine of negative 2x divided by negative 2 plus c, and our last one is going to be negative cosine of 17x plus 5 divided by 17 plus c, which was the same thing that we got here. We divided by 1/3, negative 1/2, and 1/17. So if we continue to our last row, we're going to get something very, very similar. So the antiderivative of cosine is sine, so we're going to get sine 3x over 3 plus c. We're going to get sine of negative 2x divided by negative 2 plus c, and sine, the antiderivative, sine 17x plus 5 all over 17 plus c. So we can do the U-substitution each time, but in this case, it will make our life a little bit simpler if we observe that pattern. So that pattern's also going to come up a lot in Calc 2. It'll save us a lot of time in doing certain integrals. All right, let's move on to our next example. So we wish to evaluate the following integral. So we have the integral of e to the 1 over x divided by x squared dx. So we look for our thing that's inside, and our inside function this time is going to be 1 over x. So we have u equals 1 over x, and we can move the x from the denominator into the numerator by writing it as a negative 1. So then that would give us du is equal to negative x to the negative 2 dx, which would then be same as negative 1 over x squared dx. So solving that for dx, we would multiply both sides by negative x squared. So, and when we do so, we would get that dx is equal to negative x squared du. So we substitute into our integral, and we have e to the u over x squared times negative x squared du. So our x squareds reduce out, and we get the integral, pull our minus sign out in front, e to the u du. So then that gives us negative e to the u plus c, which is negative e to the 1 over x plus c. So the antiderivative of e to the 1 over x divided by x squared is negative e to the 1 over x plus c. All right, so you try time again. All right, so for u try number 3, we need to pick our u. So we want to identify a function that is inside of some other function. So in this case, we notice that the cosine is inside the cubing function. So we'll try u equals cosine x, then du is equal to negative sine x dx. And if we divide by negative sine x and we divide by negative sine x, we get negative du over sine x is equal to dx. So substituting into our integral, we would have cosine is u, so u cubed, sine x, and then dx is negative du over sine x. Our sine x's reduce out, and we can pull the minus sign all the way out in front of our integral, and we have the negative of the integral of u cubed du, which gives us negative u to the 4th over 4 plus c. So that's negative cosine to the 4th of x divided by 4 plus our arbitrary constant c. All right, let's keep going. So example number 6. Looks a little scary at first. So we're going to want to use some algebra to simplify this. So we may need to use algebra and the properties of integrals to simplify. So first thing we can do is we can split it up into two different integrals. So 5x all over 3 plus 7x squared dx plus the integral of sine x over cosine x squared dx. So that's our property of integrals, that if we have an integrand that has a plus or a minus sign in, we can just split it into multiple integrals. So then on the next one, I have a constant multiple of 5 I can just pull out. 7x squared dx plus, here I have sine divided by cosine squared, which if I really wanted to, I could write it as sine x over cosine x times 1 over cosine x. And sine over cosine gives us a tangent, and 1 over cosine gives us secant. So that's going to give us a secant x tangent x dx. So now we need to start trying to integrate this. So here, in our first one, we're going to pick u to equal 3 plus 7x squared. Then our du is going to be 14x dx. And we divide by 14x, and we divide by 14x, and that gives us dx is equal to du over 14x. The second one is actually really straightforward, because if we just go to our integral sheet, we'll notice we have a secant tangent. And what is the integral of secant tangent? Secant x plus c. So this guy is just going to be done from our integral sheet. So after rewriting that using algebra, we're just going to get secant x for our antiderivative. But we need to keep integrating this next one. So we have 5 times the integral of x over u times, and then our dx is du over 14x. Our x's cancel, plus our secant x plus c. And we've already done that antiderivative. So now we can pull our 14 out, and we have 5 over 14 times the integral of 1 over u du plus secant x plus c. And we look at our integral sheet, and what's our integral of 1 over u? Well, 1 over u, or 1 over x, is the natural logarithm of the absolute of x, or in this case u, plus secant x plus c. And finally, our u was 3 plus 7x squared. And we could drop the absolute values, because 3 plus 7x squared is always going to be positive, because x squared is always positive, and a positive times a positive is a positive, and a positive plus a positive is always positive. But if you put them in, it's not wrong. And that would be our solution to that problem. All right, so let's take a look at our next example. Actually, one last note. So on this, we did this integral and we used some algebra to rewrite it. And we got that the integral was secant x, right? It's worth noting the integral of sine x over cosine squared x dx can also be done using a U-substitution. And if we let u equal to cosine x, then du would be negative sine x dx. Or, solving for dx, dx is equal to negative du over sine x. So if we substitute that in, cosine is our u squared, times negative du over sine x. Those reduce out, and we would get the negative of the integral of 1 over u squared du, which is the same as the negative of the integral of u to the negative 2 du. So now we would use our polynomial rule. So we have our negative from here, and then we would add 1 to the exponent and divide by it. So negative 2 plus 1 is negative 1, divided by negative 1 plus c. Minus minus would make it a plus positive, so we would get 1 over u plus c, but our u is cosine, that's 1 over cosine x plus c, but 1 over cosine is secant x plus c. And it's worth noting that that was exactly the same thing we got when we did it the other way. So this is what I was hinting at earlier. With integrals, there's going to be a ton of different ways to do that. So if you saw that U-substitution and you used it, notice instead of algebra, you get the same correct solution at the end. So this is especially helpful when you're working with someone else that you both might be doing the problem correctly, just in a different way. And that's perfectly fine. All right. So let's take a look at example number 7. So we wish to evaluate, and in this one we're going to see a slightly different technique. So we notice that our inside function is x minus 1. So that suggests we pick u equal to x minus 1. Then we take our derivative. In this case, du is going to be the same as dx. And we're going to need to calculate our limits of integration. So u of 1 is going to be 1 minus 1, which is 0. And u of 2 is going to be 2 minus 1, which gives us 1. So those are going to be our new limits of integration. So we substitute in. So u of 1 was 0, so we have 0. U of 2 gives us 1. We have x times the square root of u, but then du equals dx, so we get du. And we look at this and we're like, well, I have x's and u's, so this usually means that we picked the wrong u. Sometimes we can use the u equation to substitute out any remaining x's. So we have the equation u equals x minus 1, and if we add 1 and we add 1, that gives us that u plus 1 is equal to x. So x is going to be the same as u plus 1. So then we would have the integral from 0 to 1 of u plus 1 times the square root of u du. This won't always be possible, but if we end up in a situation where we have a mixture of x's and u's like this, it's worth looking into, can we substitute out any remaining x's using our original u substitution? So the square root of u is the same as u to the 1/2. So we distribute that into our parentheses, and u times u to the 1/2 is u to the 3/2. U to the 1/2 times 1 is u to the 1/2 du. So now we can do our antiderivative. So we add 1 to our exponents, so that's u to the 5/2, and then we divide by it, divided by 5/2, plus 1/2 plus 1 is 3/2 divided by the 3/2. And then we want to evaluate that from 0 to 1. So cleaning this up a little bit, that is 2/5 u to the 5/2 plus 2/3 u to the 3/2 evaluated from 0 to 1. So that's going to be 2/5 times 1 to the 5/2 plus 2/3 times 1 to the 3/2 minus 2/5 times u, or 0 to the 5/2 plus 2/3 times 0 to the 3/2. And those are particularly nice because 0 times anything is 0. And 1 raised to any power is just 1. So we get 2/5 plus 2/3, which then we could simplify, common denominator of 15. So this guy would need 3/3, 5/5. So 6 plus 10 would give us 16/15. So the value of that integral would be 16/15. So this technique is just something to keep in mind, that if you do your substitutions and you still have a mixture of x's and u's, before going to pick a different u, see if we can substitute out using our original u substitution any remaining x's. All right, so now we're going to switch gears a little bit. We're still going to be talking about integrals, but we want to remind ourselves about even and odd functions, and then we're going to talk a little bit about some of their properties. So by definition, a function is even if f of negative x is equal to f of x, and graphically an even function is symmetric with respect to the y-axis. So in terms of our pictures, if I draw an even function, it would look something like, well, that's a terrible symmetry, but that's the idea. Something like this, where it's the same on both sides. An odd function, it has the form of f of negative x is equal to the negative of f of x. So in terms of a picture, a function is odd if it would look something like this. Both of these suggest something. So then if I were to have the value negative a and positive a, and I was trying to find the area underneath the curve, well, since this graph is symmetric, that would mean the area to the left of the y-axis would have to be the same as the area to the right of the y-axis. Similarly, if I had negative a and a here, if I have an odd function, the symmetry would look like this. These things would have the same area, but we know that if area is above the x-axis, this is positive, and if area is below the x-axis, we know that it's negative. So then, this gives us at least a basic idea of why the following theorems are true. So our first theorem says, if f of x is an odd function, then the integral from negative a to positive a of f of x has to be 0. Well, if we look at our picture here for our odd function, the area to the left of the y-axis in this picture would be negative, and the area to the right of the y-axis would be positive. And since they're equal, but one's positive and one's negative, when you add them up, you would get 0. Well, let's formally prove this instead of a proof by picture. So if we start with the integral from negative a to a of f of x dx, using our properties of integrals, I could split this into two separate integrals. The integral from negative a to 0 of f of x dx, plus the integral from 0 to positive a of f of x dx. And now, if I make the U a U-substitution, if I let U equal to negative x, then du is equal to negative dx, or dx is equal to negative du. If I substitute that only into the first integral, I would get the integral. I change my limits of integration, so negative a, so I'm going to have the negative of negative a, and then I'm going to have negative 0 for my upper limit of integration, and then I'm going to have f, and if I solve this for x, it's going to be f of negative u, and then dx is the same as negative du. Plus, I'll leave this one alone, the integral from 0 to a of f of x dx. So now, simplifying up a bit, minus minus a makes it a and 0. I have a minus sign I can pull all the way out in front. And then I have f of negative u du plus the integral from 0 to a of f of x dx. But by hypothesis, f of x is an odd function. If a function is odd, f of negative x is the same as the negative of f of x. So by odd, we're going to have the negative of the integral from a to 0 of negative f of u du. And once again, our minus minus makes a plus positive. So now these two things are almost the same, but my limits of integration are upside down. And if I reverse the limits of integration, it changes the sign of the integral. So this would become the integral from 0 to a, but change it from positive to negative, f of u du, plus the integral from 0 to a of f of x dx. And this is a dummy variable, so these two things are the same, one positive, one negative, so they add up to 0. So this proves that the integral of an odd function on a symmetric interval always has to be 0. And we probably believed that just from the picture. So I won't do a proof for the even one, but based on this picture, what would we guess would happen to the integral? If you're interested in the proof, it works almost exactly like the other one, except for in the step where you substitute, you're going to do even instead of odd, and then exactly the same thing happens. So in this case, what happens when a function is even, instead of getting 0, as we saw in the picture, this area and this area is the same, so I could just calculate the integral from 0 to a and then multiply it by 2, which is exactly what our theorem says. If f of x is an even function and a is any real number, then the integral from negative a to a of f of x dx is equal to twice the integral from 0 to a of f of x dx. Both of these can be helpful in simplifying and working certain types of integrals. So we have some properties of even and odd functions that we may or may not remember. So recall, a polynomial is odd if all of its exponents are odd, and a polynomial is even if all of its exponents are even. That is true for monomials, and we can break up polynomials into monomials, which will also be useful. And recall, too, that sine is an odd function and cosine is an even function. And then we have the following property for the product and quotient of even and odd functions. An odd times an odd, or an odd divided by an odd, will give you an even. An odd times an even will give you an odd. And an even times an even will give you an even. So odd and even functions behave like positive and negative 1 under multiplication and division. So odds are like negative 1, so a negative times a negative is a positive. A negative times a positive is a negative, and a positive times a positive is a positive. All right, so now that we have this laundry list of things, let's go ahead and evaluate a couple of these. So example 8 says, evaluate the integral from negative 10 to 10 of x cubed dx. Well, x cubed is an odd function from negative 10 to 10. So according to our theorem, the integral of an odd function on a symmetric interval is 0. And if you did it, just the antiderivative of x cubed is x to the 4th over 4. And then if you evaluate that from negative 10 to 10, that is going to be 10 to the 4th over 4 minus negative 10 to the 4th over 4, which is going to be 10,000 over 4 minus 10,000 over 4, which indeed gives us 0. So even if you just do it the long way, you will get the correct answer. But noticing when functions are even or odd on symmetric intervals will save you a ton of time. And as we'll see in our next example, it can often take complicated integrals and turn them into something very simple. So at first glance, if we had to do or find the antiderivative of this, that's going to be crazy because it's got a whole bunch of different parts to it. But we'll notice we have a symmetric interval from negative 8 to 8. This is odd. Sine to the 16th is even, or x to the 16th is even, but sine is odd, and an even times an odd gives an odd. This is an odd times cosine, which is even, so odd times even gives an odd. And finally, x squared is even. So then we know that the integral of an odd function is 0, so this is 0. That product is 0, that's 0, and this guy is even. So this all reduces to twice the integral from 0 to 8 of x squared dx. So using the even and odd properties, we notice very quickly that this is the same as this integral, and that is a ton easier to do. So the antiderivative of x squared is x cubed over 3. So we get 2/3 x cubed evaluated from 0 to 8. So that's 2/3 times 8 cubed. And let's see, what is 8 cubed? 2 to the 3rd, 2 to the 3rd to the 3rd is 2 to the 9th, which is 512. Times 2 is 1,024 over 3. Which makes our life a ton easier. All right, let's look at our next one. So C so once again, we have the integral from negative 50 to 50 of x squared sine x. So that's an even, and sine is odd, and an even times an odd is odd. So then the value of that integral just has to be 0. All right. It's now your turn. So let's go ahead and determine the value of this integral. All right, so for this last u try, we just need to do a little bit of analysis. So x to the fourth is even, and sine x is odd, and then we have that divided by x squared plus 1 is going to be an even. So an even times an odd is an odd, and an odd divided by an even gives us odd. So since the entire integrand is odd, we know that the integral of an odd function on a symmetric interval is 0. And we're done.